Welcome to the 26th lecture of the course Turbulence. So, before we start with today's discussion, let us talk about the previous topics we started. So, that is our turbulent boundary layer we have started talking about that in the last class, and a turbulent boundary layer, the simplest turbulent boundary layer which can be thought of, that flow over a flat plate which becomes which initially remain laminar, after that it becomes transitional and finally it becomes turbulent, okay. And and the turbulent the transition starts at about REX, this transition it start at about REX Reynolds number based on AX is approximately at 10 to the power 6, okay. So, the turbulent flow whatever talking about here, it is bit high Reynolds number flow, and if you see the velocity profile in the laminar regime, it will look like that. Then slowly as you go in the downstream direction, the profile will become slowly fuller type of velocity profile. That is all because of the fact that that due to the mixing, due to the high level of mixing in a turbulent flow, that profile will be flatter or fuller, okay. So, this is known as fuller velocity profile, okay. So, this is due to mainly the turbulent diffusion or mixing, okay. Please do understand this, okay. So, all right, then we have also talked about this in the case of turbulent boundary layer, it is continuously growing as compared to your channel flow, and this streamwise gradient is much less as compared to your one normal gradient, okay. So, this is one more important point to note for the case of boundary layer flow, okay. Then we found that or we discussed that inner law holds good even in the case of turbulent boundary layer. So, that means this is what is your relation, and this relation will give you u plus is equal to y plus, very close to the wall, just like your channel flow, u plus is equal to y plus here, okay, less than this this holds good for y plus less than 5, and then this is at about 30 to 40 y plus, sorry 30 to 50 y plus onward, this log law holds good, okay. Now, Van Rijst he gave a composite velocity profile, I mean based on the argument we have done in the last class, and this is what is this profile to cover the experimental data. If you see the experimental data, which will come like this, experimental data if you measure, it will fall like this, experimental data or DNS simulation. So, to represent this, you need a velocity profile which kind of approximate both this u plus is equal to y plus as well as that u plus is equal to this log law, okay. So, using that Van Rijst composite profile we can do so, that is what we have discussed in the last class, okay. So, today we are going to talk about the the velocity defect law in turbulent boundary layer, okay. So, that is what we would like to start it, okay. So, velocity defect law, okay. So, if you plot your velocity in terms of u plus versus y by delta, okay, let us say we will plot that u plus or u divided by this mean velocity u divided by u tau, okay. If you plot this, then it is going to come something like this, okay. So, this is what is your, let us say the free stream which is going to slowly be equal to the free stream velocity, and this is what is your y is equal to 0, okay, and increasing y, and if you put your experimental data for this or the profile, this itself can be considered your measured data, but anyway if you now consider this u plus is equal to this or Van Dyke's profile and plot in this in this plot, then your, or you just plot the log law itself. So, let me use the other color for log law. So, log law itself, you will see the log law will kind of come like this. Okay. So, that means this will be approximately y by delta 0.2, okay, around 0.2 or so. So, this is your kind of, this is your this is obtained from your log law. Okay. So, this log law, it says that from y plus 50 to this nearly about y by delta 0.2, it represent the data quite well. Okay. But later on there will be a deviation if you use log law. Okay. So, actually what Van Dyke did, he examined many experimental data, sorry, not Van Dyke, the Coles, okay, sorry, Coles, he looked at many experimental data and proposed that this particular profile u by u tau can be expressed as y by delta v, summation of these two function. Okay. This is pi by kappa and some weight function y by delta. Okay. So, he says since there is a deviation towards the free stream, what you can do, you can add this function, this particular function plus another wake function, let us say which will come something like this. Okay. So, this is your wake function. Okay. Now, if you add this log law plus this function, eventually we are supposed to get the total. So, this is what let us say plot it here. If you plot this, then this is what you will get it. That means this function plus this function, if we add, we will be able to recover the actual velocity profile. Okay. So, that is what is proposal. And why this is called wave function, because with respect to y is equal to 0, if you consider y is equal to 0 as if imagine in fact there is flow even in this side, then this profile could have been done like this, right. So, just like this. So, this is what, just like your wake profile if you remember in your turbulent wake, your velocity profile was coming like this, right. Okay. So, with respect to symmetry, it was the velocity profile was something like this. Okay. So, this due to this symmetry, due to this particular shape of this particular function, we are calling this as wake function. Okay. So, this is what the consideration to represent the total velocity profile in a turbulent boundary layer, one using this that inner law, and this is what is your wake. Okay. Wake function. So, based on experimental observation, this y by delta, it has been observed that this is can be, this particular function can be represented as sine square, this is pi by 2 y by delta. Okay. So, that means this particular function can be then written as u by u tau equals to f w y by delta v plus pi by kappa 2 sine square pi y by twice delta. Okay. Delta is the boundary layer thickness. Okay. So, here delta is the boundary layer thickness, where delta is the BL thickness. and pi, this is capital pi. So, this capital pi, let us say it is known as wake strength. This is the non-dimensional constant wake strength, which is a non-dimensional constant. K is the that 1 by kappa, its value is 0.41. So, this kappa, it is not K, sorry. So, anyway, now this is what is our, this is what is the argument of Coles, that the entire velocity profile can be added using these two function, and if we use the log law for this Fw, then this function can be written as u by u tau equals to, with the log law for this, then you can write kappa ln y u tau by nu and plus the constant b plus pi by kappa 2 ln sine square this is pi by 2 y. So, pi by pi y by 2 delta. Okay. So, now if you consider this particular equation in the free stream, now let us approximate this equation at the free stream. So, at the free stream, then this value will be u. So, at y is equal to delta, this is approximation, okay. Although at y is equal to delta it should be 0.99 u infinity, but we can consider just for approximation that at y is equal to delta, this u can be replaced with u naught, and this is then u tau, and this can be written as 1 by kappa ln y. So, y in this case then delta u tau by nu, okay, plus b plus this, please note that this pi by 2 is nothing but 90 degree, okay, and this pi I would like to mean this is as your basically that wake strength parameter, okay, which is non-dimensional constant here. So, kappa, and you see this is going to be what, pi by 2 y by delta. So, y is delta, so this is pi by 2, so this is 1. So, this is what you are going to get, okay. So, let us say this is your equation 1 and this is your equation 2, then if you subtract 2 minus, so 2 minus 1, so subtracting equation 1 from equation 2, we get what, u minus u naught, sorry, u naught minus u in this case, u tau, that is what the velocity defect we have defined earlier, if you may remember. So, then it is becoming this 1 by kappa ln delta u tau by nu plus minus 1 by kappa ln y u tau by nu this is b, then your this quantity will come out b. So, and this quantity this particular expression, instead of writing the 2 sine square, instead of writing that this particular function, instead of replacing this function with this, we can just keep this for general for more general profile. Then what we can do, we can take this out. So, that means this is pi by kappa, then 2 is going to be there minus your pi by kappa has come out 2, this one is your basically that wave function y by delta, right. Let me use this. Okay. So, this is what is your that velocity defect, okay, or velocity defect in the turbulent bound layer. Okay. So, this can be rearrange, you see this can be written as minus 1 by kappa ln, you see if we take the minus out, then this minus this, which is nothing but your, this is then going to come y by delta, okay, plus b plus this term, okay, kappa 2 minus y by delta. Okay. So, this is what is your velocity defect. Okay. So, this is what is your velocity defect. Okay. Keep it in mind. Okay. So, this particular function can be approximated for the case of turbulent bound layer with this particular form. Okay. This has been found based on many experimental data. Okay. So, this is what is our velocity defect. Now, one more important point will come out if we consider this this particular equation itself. Okay. U by u tau itself, if we consider, one interesting thing will come out, that is our friction, that is will come out our friction law. Suppose we would like to evaluate this in the free stream, then this is what we will get it. Okay. So, in the free stream our equation will be this. Okay. So, let us consider then equation 2. Okay. Equation 2, what we can write? U naught by u tau equals to 1 by kappa ln delta u tau by nu, okay, plus b plus 2 pi by kappa, right, or I can write this equation u tau 1 by kappa ln, let me use this u naught delta by nu, then what I have to do, u tau will remain here, u naught will come here. I have just taken one extra u naught, okay, plus b twice pi by kappa, or you see now this particular equation, let me do one more line. So, ln, this is what? This is some Reynolds number Re naught, let us say, or Re delta, sorry, Re delta, u naught in this sense velocity in the free stream, okay, into your this, this is nothing but your u naught by u tau, right. Plus b plus twice pi by kappa. So, see this equation, this from this equation we can solve u naught by u tau. So, from this equation we can solve u naught by u tau. So, let us say equation 3. Okay. So, the above equation can be solved for u naught by u tau. Okay. So, what is the then benefit of these solutions? Let us just find it out. So, now what is the definition of screen friction coefficient by definition the skin friction coefficient is given by tau w by tau w by half rho u naught square, right. So, this can be written as twice tau w by rho twice tau w by rho u naught square, okay. Or you see tau w by rho is square root of u tau. So, tau w by square root of tau w by rho is u tau. So, that is this is nothing but twice u tau square by u naught square, okay. Or this is essentially Cf is equal to 2 into or 2 divided by u naught by u tau whole square, okay. So, or that u naught by u tau square or u is equal to square root of 2 by Cf, you see. It should be Cf, right. Okay. So, that means essentially solving this equation 3 for u naught by u tau, solving this equation 3 for u naught by u tau, you are essentially solving Cf. Okay. So, that means you are essentially finding your skin friction coefficient. So, this is the friction law for this turbulent boundary layer. Okay. So, then Cf is very important because that is what will give us the estimate of the momentum deficit as well as the skin friction drag. So, that is what is very important parameter or variable you can call it. So, now the next point we would like to make how this Cf is related with the how Cf or skin friction coefficient is related with the velocity momentum deficit, right. So, to do that let us do one thing, first let us write the that momentum equation for or mean momentum equation for turbulent boundary layer. Okay. So, if we write this then it comes that x momentum equation basically u del x plus v del u del y plus u square bar del u square bar del x plus del u v del y. This is coming from the Rans equation, keep it in mind. So, in this particular aspect we are only interested or the flow is only statistically varying in x and y direction, not in z direction, right. So, that means minus 1 by rho del p del x plus nu del 2 u del x 2 plus del 2 u u del y 2. Okay. So, this is our x momentum. Similarly, we can find our y momentum which is actually your u del v del x then v del y plus del y v square bar plus del x u v bar equals to minus 1 by rho del p del y plus nu del 2 v del x 2 plus del 2 v del y 2. Okay. So, this is your y momentum equation. Now, if you can remember our boundary layer approximations for laminar boundary layer, for laminar boundary layer, if we apply the boundary layer approximation, then this term is going to vanish, this term is going to vanish. Okay. This is all from the boundary layer approximation. Okay. Then what else we get? we also able to be we will be able to show even this term is also of the order of 1 by RE. If you can remember the order of magnitude analysis in the case of laminar boundary layer. So, we can apply here, and finally, we will be able to get this equation, but since these statistics, turbulence statistics much smaller, the gradient of turbulence statistics can be considered, or streamoise gradient of this turbulence statistics can be considered small, much smaller as compared to the wall normal gradient. So, this particular term also can be neglected. So, if we do so, then your y momentum equation from y momentum equation from y momentum equation you will be able to write that your del v square del y plus 1 by rho del p del y is equal to 0. Okay. So, let us call this x momentum equation. Okay. So, let us okay. So, this is what let us say equation number 4, and this particular equation let us say this is equation 5 this should be equation 4 and this should be equation 5. In that case means x momentum equation is equation number 4, y momentum equation is equation number 5. Then this particular equation we can name it as equation 6 or number it as equation 6. Now, if you integrate and use the boundary condition in the free stream, see if we integrate with respect to y, then we will get v square bar plus p by rho equals to a constant which can be a function of x. Okay. So, that constant can be fixed using the boundary condition in the free stream. What is the boundary condition? In the free stream, the pressure can be called as P naught, okay, and the turbulence statistics is going to be 0 in the free stream. So, that means integrating this equation and using the boundary condition in the free stream, this particular equation can be written as integrating equation 6, we can write what v square bar plus p by rho is equal to p naught of x. Okay. Note that the pressure within the boundary layer is a function of both x and y. That is why that del p del x as well as del p del y is here, but in the free stream pressure is function of x only. Okay. So, now if you differentiate these, so differentiate these with respect to x, you can write that this plus 1 by rho del p del x, sorry, 1 by rho, 1 rho is missed here, okay, there should be a rho here. If you apply the boundary condition in the free stream, then you will get it that p naught by rho. So, that means this is going to be 1 by rho, and since it is the only function of x, we can write d p naught dx. Okay. So, this is what we can write, and let us say this is our equation 7. Okay. So, using equation 7 in equation 4, okay, using equation 7 in equation 4, we get what? We will be able to get u del x plus, one more point needs to be mentioned here, from the order of magnitude analysis this term will only be neglected in this equation, as well as the gradient of this gradient of, as I have already argued, that gradient of streamwise gradient of turbulence statistics can be considered negligible as compared to the wall normal gradient of the turbulence statistics. So, this term will also go from this equation, and replacing minus 1 by rho del p del x from this equation 7, we can write what? We can write v del u del y, v del u del y plus del u v bar del y, okay, plus let us put the value of, note here, put the value of this quantity. Actually, instead of neglecting the streamwise derivative of the turbulent intensity, let us neglect it little later. So, let us keep it here for the time being. Okay. So, that was u square bar del x. Okay. Let us keep this streamwise gradient which we have neglected there little later. Okay. So, this minus the minus of minus 1 by rho, this particular quantity can be obtained from this equation. So, v square bar del x, okay. So, minus plus 1 by rho, sorry, this is dp, okay, dx, dp not dx, it should be minus, because you are taking this term in the left hand side and you are bringing this term in the right hand side. So, and then your pressure term in the y momentum equation is going to be this, okay, plus your viscous term, that is your del 2 u del y 2 and this is nu, okay. Or you see, now what you can do, you can get this term this side and both the term applying the applying this condition that gradient, streamwise gradients of all the turbulence statistics are comparatively very small, then you can write this equation as this, okay, plus u v bar del y equals to minus 1 by rho dp naught dx plus nu del 2 u del y 2, okay. This is what you can write. Now, this term as well as this term you can combine and defining the total shear stress, total shear stress and turbulent shear stress as well as the viscous shear stress, you can get a single term. Anyway, I am not going to that details, I am just mentioning that this can be done just to save some time, and this particular term it is what? It is the pressure gradient which is existing in the free stream. So, in the free stream that Bernoulli's equation holds good. So, that means using Bernoulli's equation in the free stream, this particular term can be replaced in terms of free stream velocity. How? So, in the free stream, in your free stream, P naught plus half rho u naught, right, that is what is your is called to constant, right, or dp naught dx equals to what? This is going to be your u naught rho u naught du naught dx. U naught can be a function of x, keep it in mind. If there is a non-zero pressure gradient, then u naught cannot not necessarily that u naught is going to be constant at all x, okay. That will come from this, or what you can do, you see minus 1 by rho dp naught dx is nothing but your u naught du naught dx, okay. This is applying the Bernoulli's equation in the free stream. So, that means you can replace this term also with this term, okay, and these two term also can be combined. Okay. So, this equation then can be written as this equation x momentum equation for turbulent boundary layer finally can be written as u del x plus v del u del y plus let me just write this term as well. So, this can be equals to that can be made as okay. So, that minus plus nu. So, that is nu del 2 u del y 2 minus del u v bar del y plus u naught d u naught dx. Okay. So, that is what is your momentum equation, or one more line can be done del u del x plus v del u del y equals to, you see what I can write this this equation, let us say mu by rho del 2 u del y 2 minus del u v bar del y plus u naught d u naught dx. Okay. So, this particular term 1 by rho, if you take it out, then what you are getting, that mu. So, this particular term can be written as del y mu del u del y, right, and that means I can put this del y as rho u v. Let me write this, or other way around, just 1 minute. Plus u naught d u naught dx. Okay. So, this can be written as 1 by rho del y tau v t, right. That is what we have defined. This is the viscous shear stress, turbulent shear stress, which can be written as this equals plus this dx. Okay. So, that is what is your simplified x momentum equation for turbulent boundary layer. Okay. Now, we have already derived the von Karman momentum integral equation for the case of free shear flows. I want you utilize the using this equation and integrating this equation from y is equal to 0 to y is equal to infinity. Okay. Find out the von Karman momentum integral equation for the case of boundary layer. Okay. And if you use that equation for 0 pressure gradient boundary layer, then you will be eventually come to this particular result d theta dx is equal to Cf by 2. Okay. This will come from von Karman momentum integral equation. Okay. Okay. So, let us say this is your 6, 7, okay, let us say 8. So, equation 8, what I would like to mean, equation 8 can be integrated to get that von Karman integral equation. Okay. And that particular von Karman moment, and take this as your assignment, because that has already been done for the case of boundary free shear flows. So, I expect you will be able to do it. How to do it? Please go to that and figure it out and do it, okay, and use this von Karman momentum integral equation for the 0 pressure gradient case. 0 pressure gradient means that u naught dx is equal to 0. That means minus 1 by rho dp naught dx is equal to 0. That means pressure gradient is 0. Okay. So, there is no change of pressure gradient in the free stream. In that particular case, you know that von Karman momentum integral equation will result this particular expression, which says that momentum, what is theta? Theta is the momentum thickness. So, what it says, the gradient momentum thickness means what? It is the measure of momentum deficit. Okay. The higher the value, higher the momentum deficit, and the gradient of the momentum deficit is related with the screen friction coefficient. Means higher the screen friction coefficient, your higher the value of momentum deficit in the boundary layer. Okay. That is what it says. Okay. The more and more the flow will be retarded closer to the wall, higher and higher will be the momentum deficit within the boundary layer, as well as its gradient with respect to the x. Okay. So, or if somebody can measure this d theta dx, gradient of d theta dx in a turbulent boundary layer, he or she will be able to find out CF also, okay, instead of without using the friction law. So, this is what is the result of this analysis for the case of turbulent boundary layer. All right. Now, I do not want to go further. The turbulent statistics, if you see the turbulent statistics in a turbulent boundary layer is something similar to the statistics of the turbulent channel flow. Okay. So, for reviewing of these aspects, please refer to the book by S.B. Pope. Okay. I am not going to go in details to that. Okay. And in fact, the turbulent kinetic energy equation or the turbulent kinetic energy budget is also something similar for the case of turbulent boundary layer. Okay. I just wanted to quickly write the turbulent kinetic energy equation. I would like to stop here because I do not have much time to discuss further. So, turbulent kinetic energy equation, okay, TKE, turbulent kinetic energy equation for the case of turbulent boundary layer. If you use the general turbulent kinetic energy equation which we derived, then if you use the approximation for the boundary layer, we will be able to come to this particular equation. Okay. So, let me write this. Here K is the turbulent kinetic energy. Okay. Production minus the pseudo dissipation, then what else you get, this plus, since you are using pseudo dissipation, there should be a diffusion term here. Okay. So, dk dy. Okay. So, plus sorry, not plus, it should be minus the turbulent transport. So, the turbulent transport will be given as d dy half ui bar, v will be here minus the the pressure transport term, that is p by rho into v bar. Okay. So, these are the terms which are going to be, sorry, diffusion term, it should be I think this. Okay. So, this is the kinetic energy diffusion. So, this is what is the turbulent kinetic energy for the case of turbulent boundary layer. Okay. And if you plot very close to the wall, the way we have plotted for the channel flow, okay, it will come like this. So, let us say this is y plus is equal to 50. Okay. Y plus is equal to 50 and this is let us say 0.2 and let us say this is also your minus 0.2. Okay. And this is your loss, this side your loss and this side is your gain. Okay. This is gain and this is loss, and if you plot this, if you plot this, is going to come, for example, production will come like this, okay, and your diffusion term will come something like this. Then your pressure transport term will be something like this, okay, and your dissipation term, okay. So, dissipation term will be something like this. This is what is your dissipation term, this is your production term, this is your dissipation term, this is your dk dy2 this viscous diffusion term, this is the pressure transport, and the last one which is going to be there, that is your turbulent transport, which is going to be something like this, okay. So, it is something very similar to the turbulent channel flow, and this particular part, this mean flow or convection, okay, this is actually negligible very close to the wall. This will be almost 0 close to the wall, but it will be significant as you go towards the outer side, that I am not drawing here, okay. So, with this I would like to stop here, stop the discussion on turbulent boundary layer. Now, that a little bit one more part is left, that is what is our general energy cascade as well as the Kolmogorov hypothesis. So, these are the two topics we need to discuss now, okay. So, with these discussions on turbulent boundary layer, here we are focusing our discussion on energy cascade, and Kolmogorov hypothesis or hypothesis plural, okay, because there are 3 hypotheses. So, that is what is the topic of discussion at this point of time. So, we have learnt that any turbulent flow is going to be full of scales. For example, if the flow is going through within a turbulent channel, then the biggest scale will be of the order of the width of the channel to the smallest dissipation scales. So, there will be various scales, or you can say various scales or eddies of various length are going to be there in any turbulent flow you consider, either in your turbulent boundary layer or in turbulent wake or in turbulent jet. Anywhere you will have different sizes of eddies, and as I have mentioned earlier, eddies means a coherent packet of turbulent motion which is correlated, highly correlated within this length, okay. So, that is what can be considered or loosely can be considered as turbulent eddy, okay. That is what has been mentioned earlier, which can be considered as a particular turbulent length scale, alright. Now, we have learnt that due to the nonlinearity, there will be generation of many scales in a turbulent flow, okay. And we have also discussed that energy enters, energy gets extracted at the large scales, or large scale extract energy from the mean flow, then it cascades down to the smaller and smaller scales, okay. So, alright, there are couple of questions which are not answered, which Kolmogorov actually quantified and put forward his theory in terms of 3 hypotheses, okay. That will be our discussions. So, before we proceed, this energy cascade was first discussed by Richardson, okay, in 1922. So, according to his notion of this energy cascade, he considered a bigger turbulent eddy is somewhat unstable, since a bigger turbulent eddy can be considered of high Reynolds number. For example, suppose in a turbulent flow we have, as I said, in a turbulent flow we can have various sizes of eddy. So, this is what if is this if we represent this is the bigger eddy and its length let us say of approximately L and its velocity is UL and time scale is actually your L by UL. Okay. So, for this particular eddy then Reynolds number if you define for this eddy which will be your U L by nu. Okay. So, if the eddy size is large anyway we can consider this Reynolds number is also large because the velocity scales of the largest eddy can be considered of the order of the URMS velocity existing in that particular turbulent flow. So, in that case Reynolds number can be considered to be pretty large. So, if Reynolds number is large then your viscous effect is less there and your inertia effect is dominating, that is what it says. If this is the case then Reynolds number is large means what? The flow is prone to instability. Okay. So, that means his notion is that this bigger eddy will break it to smaller eddy and then that smaller one again will break it to even smaller one and so on to the smallest scale. Okay. So, he picturized that particular idea this bigger eddy, then from that there will be another smaller one. Okay. The bigger eddy will break it into a smaller one and this smaller one is going to break to even smaller and this smaller one again it is going to break it to smaller one and so on to a smallest one where it will get dissipated by the effect of viscosity. That is what is the kind of energy cascade picture put forward by Richardson. Okay. So, this is the kind of cascade put forward by Richardson. Okay. So, this notion of energy cascade. Okay. So, this in fact he put in terms of poetic language. So, what he did, let me just write that quickly. This particular cascade Richardson put poetically like this: big holes have which feed on their velocity and little walls have lesser walls and so on to viscosity. Okay. This is in a molecular sense. So, this has been this is the picture put forward by Richardson. Okay. So, now all right, as per his idea, this all good, that bigger eddy will break to smaller one, the smaller one again it will break to even smaller one and so on to viscosity. The question comes, then what is the smallest size where it is going to be dissipated? Okay, this is unanswered. All right. Another, when the scales are becoming lesser and lesser, what about their velocity scale? What about the time scale? Is the velocity scale is same or it is also changing? So, these are the questions which are not answered. Okay. So, Kolmogorov then came in picture and he quantified this, what should be the smallest scales where the dissipations are happening, okay, as well as your kind of the velocity scale, how it should vary with changes, I mean whether it should reduce, increase, decrease as your this length scale is decreasing. Okay. So, these points are put forward by Kolmogorov as his hypothesis. So, let me just write this hypothesis as quickly as possible because I have very less time. Kolmogorov's hypothesis of local isotropy. Okay. So, this is his hypothesis of local isotropy. So, let me write the statement at sufficiently large Reynolds number the small scale turbulent motions are statistically isotropic. Okay. So, what he says, in a turbulent flow there can be range of scales, right. So, there are some scales which are smaller as compared to the biggest scales. If you consider their velocity statistics or any other turbulent statistics, okay, these statistics are statistically isotropic. It does not depend on the coordinate system. Okay. That is what it says. Okay. So, this is his first hypothesis. All right. Now, it says that okay, there are some scales which are statistically isotropic. For example, if we draw a picture, that will be better to visualize what he would like to put forward. So, let us say the biggest scale is given by of size L naught and corresponding velocity scale U naught, the biggest scale, and he is talking about a length scale, small length scale or smaller length scale. Let us say this is your the demarcation length, EI may be considered approximately it may be L naught of divided by 6, and let me just complete it, after that I will discuss. And this particular regime, universal equilibrium range, okay, and this particular range is known as inertial range. And this is your dissipation range, okay, and this is the demarcation for let us say LDI, okay, and somewhere here let us say your eta Kolmogorov scale, I will come to that. Okay. Let this picture be there and let me discuss, and this site is large eddies which are anisotropic in nature. Okay. So, these are large eddies, okay, anisotropic. Okay. So, the large, what he says that below this length scale, below this, let us say this is the maximum length scale in a flow, and there are many length scale. At any point you take, you will get one length scale in that flow. So, at smaller length scale, let us say below these, the statistics, of these scales, if you consider locally, you should not consider the, statistics of related to the large eddies, then statistics of these scales are actually isotropic. Okay. All right, this is fine. Now, the question can be asked, all right, they are isotropic, they do not depend on this orientation of the axis, that is fine, but what about the parameters that do depend, what about the parameters the statistics depend on? Okay. So, that is the next question comes. So, to answer these particular questions, he come up with the second hypothesis, okay, which is known as Kolmogov's first similarity hypothesis. Okay. Is first similarity hypothesis. Okay. So, let me once again write the statement of this. In every turbulent flow, at sufficiently large Reynolds number, the statistics of small scale motions, okay. Small scales means that scale which is less than your L naught, okay, that is what it says, okay, or in this particular case less than E I, okay, have statistics of small scale motions have universal form and the statistics universal form have statistics and are uniquely determined by uniquely determined by the parameters epsilon and nu. Okay. So, this is what his second hypothesis, okay, where he says that in every turbulent flow at sufficiently large Reynolds number, the statistics of small scale motions, the small scale motions means the scale which is in this regime are have universal form, okay, and are uniquely determined by the parameters epsilon and nu. Okay. That is what is the point here. And how he come up with this maybe can be explained using this Richardson idea. So, Richardson idea says that this bigger eddy comes to a smaller and smaller, smaller and smaller. So, what it says that energy is getting transferred from this big eddy to smaller one, this smaller one to even smaller and so on, right. So, there are two things which is important here. One, the energy transfer rate, okay, which is determined by. So, that means that at rate energy is transferring, at the same rate dissipation is happening, right. So, this is important. That means this this balance is mainly governed by two things, then that rate, dissipation rate, epsilon, and of course viscosity, okay. So, these are the two parameters which are then very very important, okay. Now, based on this hypothesis, there are two important identities which can be found, okay. So, first what we can do, using these two parameter we can then define the scales, okay, define the velocity, length and time scale, okay, and this is can be defined as, these are known as Kolmogorov scales, okay. So, these are that length scale, Kolmogorov length scale eta nu cube by epsilon, and velocity scale u eta is equal to epsilon nu 1 by 4, okay. So, this is and your, let me write first, and your time scale tau eta is actually nu by epsilon half, okay. So, if we define a Reynolds number based on these scales, then what is going to come? It should be 1, okay. So, that means if we define the Reynolds number based on that Kolmogorov scale, which is eta u eta by nu, what it is coming, let us see. So, that is basically your you see that nu. So, this is essentially nu by nu, which is equal to 1, okay. So, this is one identity which is coming out from this hypothesis. Another, so this identity let us first discuss. So, what it says that the Richardson idea, okay, what was the idea? That larger scale will have large Reynolds number, okay. They will prone to instability, they will break it to smaller one and so on to viscosity. So, in this cascading process, then what is happening, as you are coming smaller and smaller scale. So, essentially your Reynolds number is also reducing, right, because the scale is becoming smaller and smaller. If Reynolds number is reducing, means what? Your viscous effects is also going to be dominating, because why? Reynolds number is defined as inertia force by viscous force. Since the Reynolds number is reducing, that means your viscous force is getting dominated, okay. So, that is what it says, right. So, here Reynolds number is very small. So, Reynolds number is 1, means what? Viscous force is really dominating in this case. That means that these are the scales where dissipation is going to happen. That is what it says, okay. And this is what is your time scale. So, this time scale, so let us see whether it is coming correctly. This is nu meter square, this is basically your this is meter square per second, yeah, this is meter square per second, and this one meter square by second cube, right. So, so that will get cancelled, and this is meter square per second, and this is meter square per second cube. So, that is fine. Okay. So, this scale is fine. All right. So, this is one identity you get. Another point, the dissipation, the rate of dissipation. So, rate of dissipation, we can, what is our rate of dissipation? Epsilon, and epsilon is equal to twice nu small Sij bar, if you can remember. So, that means the dissipation epsilon can be of the order of what, nu into this u eta by eta, right, u eta by u eta square. So, which is nothing but your nu into 1 by tau eta square. So, what it says actually, this velocity gradient can be characterized by this ratio. Okay. So, this particular velocity gradient can be characterized by this particular ratio. All right. With this, now we can do one more important observation. So, let us do it. So, from the first hypothesis we got two important identities. One is Reynolds number 1, and another is this particular the ratio can be used to characterize the velocity gradient. Okay. So, I am sorry to mention that we need to change the room in between. So, that is the reason it may so happen that it is not so clear, but anyway the idea is that the first two identities are coming from this first hypothesis, sorry, these two identities are coming from the first hypothesis. All right. Now, if we define see this epsilon, then the dissipation can be written as this, right. So, this epsilon is what, that can be this is of this order, that is what we have learnt, and this then just now whatever we learnt, that u eta divided by eta square, right. I mean, so this quantity then is this side is going to be order of this. Okay. So, from this what we find, you see that L naught. So, essentially let us do this ratio. So, u naught cube L naught then equals or is order of what, nu u eta square by eta square, right, or let us take this eta square here and L naught square, right, and so this is eta square L naught square, and this can be written as nu by u naught cube, okay, L naught eta square. Okay. So, so we need to do a little bit manipulation. So, let us write this as eta square, let us say sorry, eta to the power 4 and L to the L naught to the power 4. Let us see what we get. Okay. So, that means nu, here what we have done, we have so that means u eta square and eta 4, that means eta square will come here, and let us say with nu square, and one nu square you take it, and L naught was there. So, this is going to be the L naught 3, right. So, so you see from this what you get. So, u naught cube I have missed it, right. So, u naught cube should be here. So, you see that means that eta by L naught 4 is equals to, you see, u eta square by nu square, which is nothing but your 1, because this is Reynolds number based on Kolmogorov length scale and velocity scale, which is equal to 1 from identity. That means we are left with nu cube by L cube u naught cube. So, this is essentially we are left with 1 by Re, okay. Re is based on this length scale u naught cube, right. So, this is, so essentially we are getting eta by L naught of the order of Re minus 3 by 4. Okay. So, this is what we get it from this, okay. Because why? Dissipation, rate of dissipation can be replaced with this, because what we said, that energy which is entering at the larger scale, that rate is fixed, the rate at the same rate it is going to be dissipated. So, this epsilon can be estimated by this expression. So, from this we get that ratio of the Kolmogorov length scale to the largest scale in the flow goes by this relation. Similarly, that velocity scale u naught, this will go as 1 by 4, and tau eta by tau, this goes by 1 by 2. Okay. So, this relation, if you see very minutely, one important thing comes out. See, as you increase the Reynolds number, this ratio becomes smaller and smaller. What does it mean? That scale separation, this range, this eta and this L naught, this range gets wider and wider. Okay. Similarly, this also says whenever you are increasing the Reynolds number, the separation between the velocity scales also changes as well as the time scale. And not only that, this also says that velocity scale and time scale decreases with decrease of the eddy sizes, okay, which we pose as a question at the beginning. Okay. So, that also this relation shows. All right. Now, that another argument which comes in picture is that since with increasing Reynolds number, this range between this eta and L naught is increasing and increasing, in between then there will be some scales which will be far away from this eta, which will also be far away from this. Okay. So, in between you will get a range of scales which will be independent of viscosity. So, that was his argument, and which he has put this particular argument in terms of his second similarity hypothesis. So, what we are going to talk about, Kolmogorov's second similarity hypothesis. Okay. So, it states that in every turbulent flow, at sufficiently large Reynolds numbers, the statistics of the scales L, L naught and eta have universal form and are uniquely determined by epsilon independent of nu. Okay. So, this is what is his second similarity hypothesis. So, essentially this is the range he is talking about, this particular range. If you see this particular range, in this particular range your L is much less than your L naught, is much greater than your eta. In this particular range then the statistics are determined by epsilon, not by nu. Okay. Whereas, in this particular range statistics are determined by epsilon and nu both. Okay. So, that is what is his argument. Okay. And this comes in the second similarity hypothesis. So, in this particular case, if you see the energy that associated with a particular length scale can also be expressed as. So, let me just quickly give you an overview of the energy spectrum relation, okay, obtained from this first similarity hypothesis. So, using first similarity hypothesis, it is possible to arrive at this relation C epsilon 2 by 3 k minus 5/3, okay, where C is a constant and k is wave number. Okay. That means k is equal to 2 pi by lambda or L you can consider here. Okay. So, in this regime this particular relation holds good. Okay. So, what in this particular regime, inertial range, this energy that energy spectra is given by this particular relation. This comes from the Kolmogov's hypothesis only. Okay. So, if we plot this spectra in a turbulent flow, usually it will let us say logarithmic of k, or in log scale if you put, and this is your log of E of k. Okay. Then it usually comes as like this. Okay. And this particular regime is basically is known as k is equal to minus 5/3 regime. Okay. That you can see, I mean, from this relation itself. Okay. That in this particular regime you will see your dissipation for a constant dissipation and constant C, you will see that k varies as minus 5/3. This is the relation. If you just get it log in both the sides, this is what you will get it, right. So, in fact, you can in fact you can check this with the data sent to you, okay, the measured data which is already shared with you, both hardware and the PIV measurement data in a turbulent boundary layer. You can use these data to find out this particular scaling aspect. You will see there is a small layer of minus 5/3 regime, okay. And this particular plot is in wave number, and so that also can be that frequency plot or this the relation between the frequency spectra and the wave number spectra can also be found from the Taylor series the Taylor hypothesis. The hardware data which was sent to you to see or to plot in terms of this wave number, you have to use this Taylor hypothesis which says which is based on actually frozen turbulence scale. For example, some turbulence scales are there, let us say these are the turbulence scales in a flow, and these turbulence scale, if we consider they are not doing anything, they are just convecting with the flow, okay. So, if you have a spatial series, that spatial series can be converted into time series, or if you have a time series, the time series can be converted into a spatial series using the Taylor hypothesis, okay. Using the Taylor hypothesis is frozen turbulence, okay. That is what. So, that this relation is given by this u naught or u into del x, okay. So, the time derivative of a quantity can be related with the this is the velocity of convection with the spatial derivative, okay. So, this is what the idea of Taylor hypothesis. Using this you can actually plot your hardware data itself in terms of wave number, okay. So, you can do it at your hostel at your when you get the time, okay. All right. So, this is what I would like to talk about briefly, and we do not have any more time to discuss further in this particular course for this given semester, okay. So, I would like to stop it here, okay. Thank you.